In today's lecture, we'll start by giving examples of Gaussian elimination to solve systems of equations. So our first example is the following. Solve the system of equations x1 minus 2x2 plus 3x3 is equal to 7 minus x1 plus x2 minus 2x3 is equal to minus 5, and 2x1 minus x2 minus x3 is equal to 4. Okay, so there's a system of equations, and we'll try to solve these. Okay, so the first step is we write down the augmented matrix. So the augmented matrix is 1 minus 1 2 minus 2 1 minus 1 3 minus 2 minus 1 and 7 minus 5 4. Okay, so this is the augmented matrix. And so this part here comes from the coefficients of the xi's. So from the left hand side, this is the matrix A. Okay, we're going to do row operations to this so that A is transformed into a row echelon matrix. So we'd like to get a 1 in the first 1 1 entry. Okay, there's already a 1 here if you notice. So actually, we already have a leading 1 here, and below the leading 1 we want to get zeros. So let's apply some row operations to get zeros below that. So if you add row 1 to row 2, and also that will put a 1 below the leading 1. It will give a 0 in the second row, and if you want we also want a 0 in the third row, so we should multiply the first row by minus 2 and add that to the third row, and that'll be a new third row. Okay, so this will be our new augmented matrix. So if we work that out, we get zeros below the leading 1, and then the terms here are as follows: minus 2, minus 1, 3, 3, 1, minus 7, and to the right of the vertical line we have 7, 2, and minus 10. Okay, so we've dealt with the first the first column. So we have a leading 1 in the first column, and below the leading 1 they're all zeros. Okay, so now we go to the second row, and we want a leading 1 in there. So the first non-zero entry is a 1. We can make that into a leading 1 by multiplying by the second row by minus 1. So this will be our new second row. And we get 1 minus 2, 3, 0, 1, minus 1, minus 2, and the last row we didn't do anything to it yet. Okay, so that's our new augmented matrix. So we have another leading 1 here. Now below the leading 1 of the second row we want to get zeros. Okay, so the obvious thing to do is multiply the second row by minus 3 and add it to the third row. and that will be our new third row. Okay, so when you carry that out, your first row stays the same, and the second row stays the same, and the third row it's transformed into this. I just made a mistake here. So the last two entries, when you multiply the second row by -3 and add it to the third row, you get -4 here, -4 and -4 here. Okay, so finally we want a leading 1 in the third row also. So here, if you multiply by -1/4, okay, so our matrix becomes this. Okay, if you notice, we have a leading 1 in each of the, so we have 3 leading 1s here, leading 1 in each column. So this matrix here, this matrix is in row echelon form. Row echelon form. Okay, and so we've completed the second step of the algorithm, the Gaussian elimination algorithm. Okay, so the third step states that the third and fourth steps, they state that we should look at the columns and see which ones have leading 1s and which ones do not. Okay, so each of these 3 columns has a leading 1. So this means that there are no free variables. So there is no column without a leading 1. There are no free variables. No free variables. And if we write down what this augmented matrix corresponds to, the system of equations that it corresponds to is the following. So we have x1 minus 2x2 plus 3x3 equals 7, x2 minus x3 is equal to -2, and x3 equals 1. So the way we now try to find the set of all solutions of this. And the way we do this, we work backwards from the bottom row. So we start with the bottom row. The bottom row tells us that x3 is equal to 1. And then we look at the second row. That tells us x2 is equal to x3 minus 2. When you put x3 equals 1, you get -1. So this is 1 minus 2, which equals -1. And finally, the first row tells us what x1 is. So x1 is equal to 2x2 minus 3x3 plus 7. When you put x2 and x3 in there, so we get x minus 2 minus 3 plus 7, and this is equal to 2. Okay, so we get x1, x2, x3 like this, and we can see that there are no choices here. There are no free variables, so there are no choices here. And we see that we have a unique solution. So the unique solution is x is equal to So x1, x2, x3, which here is 2, minus 1 and 1. So this is the unique solution, and it's easy to check that this is a solution. If you just plug this into the original equation, it satisfies it. So this is a solution, and the method shows us that this is the only solution. This is the unique solution. Okay, so here's a second example. So let's discuss solutions of the system. x1 minus 2x2 plus 3x3 is equal to b1 minus x1 plus x2 minus 2x3 is equal to b2, 2x1 minus x2 plus 3x3 is equal to b3. So here where b3 are parameters, so where the bi's are parameters, where b1, b2 and b3 are parameters. Okay. Let's carry out Gaussian elimination on this to solve this system. So first we write down the augmented matrix. So let me just write it down here. So the augmented matrix is so we write this down, and this is 1 minus 1, 2 minus 2, 1 minus 1, 3 minus 2, 3, b1, b2, b3. Okay, so this is the augmented matrix of this system. And we want to apply Gaussian elimination to this. So Gaussian elimination, again, we're in good shape. We have a leading one here. I mean, if we'd had a 0 here in the 1, 1 entry, we would look below that in the first column. If the first column was identically 0, there's nothing we could do, and we would look in the second column. If there had been a 1 in a lower down in the first column, then we could switch rows, and if there was a non-zero entry somewhere else in the first column, we could switch rows, bring it to the first entry, and then rescale it to be 1. Okay, so that's the general strategy. Here there's a 1 in the 1, 1 entry. This is our leading 1, and we want to get zeros below that. So what do? We take row 1 and add it to row 2, and that'll be a new row 2, and you multiply by 2, row 1, and add it to row 3. That'll be a new row 3. Okay, so what do we get here? So we get zeros below the first leading 1, and then the second column and the other columns also change appropriately. So we get minus 2, minus 1, 3, 3, 1, minus 3 here. And the last column also changes, b1, b1 plus b2, and minus 2, b1 plus b3. Okay. So that's what our augmented matrix changes into. So now we look at the second row in particular, or rather the second column, and we want to get a leading 1, hopefully in the 2, 2 position. Yeah. So the second row is is non-zero, and we have a non-zero entry in the 2-2. The 2-2 entry is non-zero, so we can make this into a leading one just by multiplying the second row by -1. Okay, yeah, again, I mean, if in the second column below the first entry there had been all zeros, then we'd have to look for a leading one in the third entry of the second column, and so on. So it should be fairly clear what one does. So we multiply by -1 the second row, and we get our leading one in the second row. So this is -1. So this doesn't change, this becomes -b1 minus b2, and the last row remains. Okay, so yeah, we have two leading ones here, and we want zeros below the leading one of the second column, of the second row rather. Okay, so we add -3 times row 2 to row 3, and we get so we get 1 minus 2 3 b1 0 1 minus 1 minus b1 minus b2, so that doesn't change. And in the third row we find we get 3 zeros here in this part, and the last entry becomes b1 plus 3b2 plus b3. Okay, so yeah, this is clearly in row echelon form. Okay, so we've completed the second step of the Gaussian elimination algorithm. So now, if we were to write down this set of equations corresponding to this augmented matrix, our third equation, note that our third equation would be 0 on the left-hand side is equal to b1 plus 3b2 plus b3. Okay, so it's clear that the system of equations can have no solutions unless b1 plus 3b2 plus b3 is equal to 0. Okay, so we find that if b1 plus 3b2 plus b3 is non-zero, then there are no solutions. So there can be no solutions, because whatever you put x, I mean, you will never get 0 with something non-zero. Okay, so there are no solutions. And in this case, we say that the set of equations is inconsistent. Inconsistent in this case, inconsistent in this case, maybe. Okay, if b1 plus b2 3b2 plus b3 happens to be 0, then there will be solutions. Okay, to investigate these, let's, for example, let's take make some choices of b1, b2, and b3. So, for example, take b1 equals 2, b2 equals 1, and b3 equals minus 5. So it's just an example, one possibility. So yeah, there are many choices of b1, b2, b3 which satisfy this, which make this equation 0, obviously. So if we take this one, then b1 plus 3b2 plus b3 is equal to 0. So then our set of equations, so the last equation is just 0 equals 0, and then the first two equations, they become x1 minus 2x2 plus 3x3 is equal to, so if you look at the equation, so it's x1 minus 2x2 plus 3x3 equals b1. So b1 is 2. And the second equation, if you look here, is x2 minus x3. So it's x2 minus x3 is equal to, on the right hand side there was minus b1 minus b2. So it's minus b1 minus b2 is minus 3. Okay, so there it corresponds to these two equations. Okay, so if we recall what the third and fourth parts of Gaussian elimination stated, it stated we should look at our row echelon matrix and we should consider which columns have leading ones and which not. Okay, so there's two leading ones. The third column has no leading one, and so this corresponds to the free variable. So free variable. So x3 is a free variable. That means this is the third column. So x3 is a free variable. And columns 1 and 2, they have a leading 1. So x1 and x2 are variables that can be expressed in terms of x3. So x1 and x2 should be variables which can be expressed, variables that can be expressed in terms of x3, of the free variables, which is just x3 in this case. Okay. Okay, so let's go back to these equations. So here, so x3 is a free variable. So let's set x3 equals alpha, for example. I mean, this is just, so alpha is arbitrary. It's a free variable. And then here the second equation tells us that x2 is equal to x3 minus 3. So x3 is alpha, so this is alpha minus 3. And the first equation tells us that x1 is 2x2 minus 3x3 plus 2. And if you plug in x2 and x3 into there, you get minus alpha minus 4. Okay, so we get x, x1, x2, x3, and this is equal to, so we had x3 is alpha, x2 is alpha minus 3, and x1 is minus alpha minus 4. And we can write this as alpha times minus 1, 1, 1, plus minus 4, minus 3, and 0. Okay, so here alpha is arbitrary. Alpha in R is arbitrary. And by construction, I mean by the algorithm, it's easy to see that this corresponds to the set of all solutions. So the set of all solutions depend on this parameter alpha. In particular, there are infinitely many solutions. So this gives all solutions of the equation, of the system of equations. Yeah, this is with our choice of b1 is equal to 2, b2 equals 1, and b3 equals minus 5. So we can see that depending on the choices of b1, b2, and b3, we either have no solution or infinitely many solutions. So the original system of equations has either no solution or infinitely many solutions. Many solutions depending on what we choose for b1, b2, b3. On the choice of b1, b2, and b3. Okay, so that's a Gaussian elimination. Both of the systems we considered were square systems in our examples. So we had two square systems. They were both 3 by 3, 3 equations in 3 unknowns. As equation 2, equation 1 was similar. You can also consider arbitrary m by n systems of algebraic equations, and Gaussian elimination gives us a method to find the set of all solutions of those. I've concentrated on square ones because these are the ones that are going to be relevant for us. However, there is an example of an m by n system, a non-square system, in the notes. Okay, so let's now consider the effect of elementary row operations on the determinant. On the determinant. Okay, and the result we're going to mention is the following theorem. So let A be an n by n matrix. Obviously, if A is not square, then we don't talk about its determinant. It's not defined. So we want to know what the effect of these 3 elementary row operations is on the determinant. And we have the following result. So we'll consider the 3 elementary row operations in turn. So a row operation. So this is type 1 row operations. A row operation of the form CRI goes to RI. So we multiply row I by C, which is non-zero. So the effect of this is it multiplies the determinant of A by C. Okay, so you start off with a matrix A, you apply this row operation, you get a new matrix. The determinant of the new matrix is C times the determinant of the old matrix. So that's what we're saying. So that's type 1 row operations. So type 2 is when we interchange 2 rows. Okay, so this one, the effect of this on the determinant is it multiplies the determinant by -1. Okay. That's type 2 row operations. Type 3, so a row operation, you multiply row I by A and add it to row J, and that's your new row J. So it turns out that this does not change the determinant of A. Does not change the determinant of A. Okay, so for the proofs of these, yeah, it's some of them 1 and 2. Perhaps you can read off. You can see they're not too difficult to see. Using here, so the definition of the determinant is given by a cofactor expansion along any row. In fact, the definition of the determinant was cofactor expansion along the first row, and I stated that in fact we could take the cofactor expansion along any row. In fact, they will prove the first two. You can see how they work, and you can prove the third as well in this way. But I won't go into the details of the proof. You can look in any linear algebra text that should have a proof of this statement. Anyway, so I'll leave it at that. So we will note from this theorem that if the determinant of A is non-zero to start with, it will remain then after a sequence of elementary row operations. It will remain zero. Sorry, it will remain non-zero. Will remain non-zero. Okay, so if it starts off non-zero, it remains non-zero. So clearly you can see here, the first one, it multiplies it by a non-zero constant. The second one multiplies by -1. The third one does nothing. So if it starts off zero, non-zero, it remains non-zero. And if it starts off zero, it remains zero. So if also if the determinant of A is zero at the start, then it will remain zero. Will remain zero after a sequence of elementary row operations. Okay. So recall what we'd said about the determinant. So the determinant tells us about the invertibility of A. In particular, if the determinant of A is non-zero, the matrix is invertible, and if it's zero, the matrix is non-invertible. So a matrix is invertible if and only if its determinant is non-zero. So we see that row operations do not change the invertibility of a square matrix. Row operations do not change the invertibility of a square matrix. Ability of a square matrix. Okay, so now I want to state a few more observations about solutions of square systems. So our examples were of square systems, and we're just going to summarize the results here. So solutions of square systems. So we're going to collect the results here. So consider ax equals b. So we have a system of equations, ax equals b, where A is an n by n matrix. Okay, so after applying a sequence of elementary row operations, I mean, let's say after applying Gaussian elimination, to the system. There are two possibilities. Oops. Okay. So what are we doing? So we start off with the augmented matrix A, B, and we apply Gaussian elimination. It becomes E, D, where E is in row echelon form. Okay, so the first possibility is that E has a row of zeros. Okay, so if E is square, and if it has a row of zeros, for example, the last row, so then there are at most n minus rows. So there are at most, so this is going to be strictly less than n rows, and so each row has only one leading one. So there are at most n minus one leading. So there are at most less than n leading ones. So we write it better, maybe at most n minus one leading ones. But there are n columns, so not every column can have a leading one. Okay, so we have a free variable. So we must have a free variable. So there are free variables. Okay, so this was the second example. It was illustrating this case. So notice here that if E has a row of zeros, in fact, its determinant must be 0. So we get, in particular, we get determinant of E is equal to 0. And this is equivalent to, we know that a sequence of, when you apply a sequence of row operations, determinant either is always 0 or is never 0. So the original matrix must have had determinant 0. Okay, and when you have free variables, as we saw, you may have, this was the second example, we either have infinitely many solutions or no solutions. So there are no solutions. So this corresponds to the case where it's inconsistent. So when you transform it, if you have some rows of 0 in E, but the corresponding entries of D are non-zero, then the system is inconsistent and we have no solutions. So, so this is if there is a row of zeros in E. Row of zeros in E, but the corresponding entry of D is non-zero. D is non-zero. Okay, so this is when there are no solutions. This is the inconsistent case. So we call this inconsistent. If that is not the case, then in fact it turns out that there are infinitely many solutions. So, or there are infinitely many solutions. Okay, so there are infinitely many solutions because there is a free variable. So we said there are free variables. So the variable can be an arbitrary. It can be an arbitrary real or complex number. So you have infinitely many solutions. Okay, so the other case is that E has no row of zeros. So what happens in this case? So 2E has no rows of zeros. So in this case, when you consider it has no rows of zeros. So this means that every row of E must be non-zero, not identically zero. And so each non-zero row in a row echelon matrix must have a leading one. So E must be like this. It must have a leading one here, all zeros below it. And there's no rows of zeros, so each row has a leading one. So there are exactly n leading ones, and they must be along the diagonal. There's no other choice. I mean, by the definition of row echelon matrices. So below this there are zeros, and so on. So we get zeros below the diagonal, and the diagonal entries are 1. And above, these are arbitrary entries. So I just put asterisk here, star, etc. These are all arbitrary entries. So E must have this form. So just by examining what row echelon matrices must look like, and using the fact that E is an n by n matrix. Okay. So what have we done? We've transformed A, B, the original equation, into E, D. So E is precisely as we've stated here, with one's longest diagonal. And then by some further row operations, so this is row operations, and then more row operations. So we have all zeros below the ones, and now it's easy to get all zeros above the ones as well. So, for example, in the second, considering the leading one in the second row, if you multiply the second row by an appropriate constant and add it to the first row, we can get a 0 above that as well. So we can get a 0 above each leading one. So in particular, we can transform it into the identity matrix. So we transform it into the identity matrix. And on the right-hand side, we will get something, let's call it Y. Okay. So we can transform A into the identity matrix by row operations. Now the determinant of I is 1, is non-zero, so determinant of I equals 1, which is non-zero. So the determinant of, in particular, determinant of A must be non-zero. Okay, so this is the case where determinant of A is non-zero. And in this case, in fact, you have the original equation, the final equation, the set of solutions of that is the same. So here, this corresponds to the equation ax is equal to b, and yeah, this corresponds to a set of equations ix equals y. Okay, ix equals y, and the only solution of that is x equals y. So you can see here, this has the unique solution is y is equal to a y. So y, the solution of this last equation of this augmented, the equation corresponds to the last augmented matrix, must be the same as the first one. So for the first equation, the solution, unique solution, is clearly x is equal to a inverse b. And so here, this must be x is equal to a inverse b. And so this is just I and a inverse b. Okay, we're saying that we can transform a b into I, a inverse b, by elementary row operations. So when you get identity before this vertical line, then you must have a inverse b after this vertical line. And so this is the determinant is non-zero, and case when the determinant is non-zero. Okay, so let me just summarize. So there are two cases. Determinant A equals 0, and you have no solutions or infinitely many solutions, or infinitely many solutions. And second case is when the determinant of A is non-zero, and here we have a unique solution. Okay, the unique solution can be read off easily by Gaussian elimination, and we know that there must be a unique solution, x equals a inverse b, in fact. So we know this already, but Gaussian elimination lets us find this solution without actually having to compute a inverse. That's what Gaussian elimination tells us about square systems. So it's interesting to consider the case where b is identically 0. So it is interesting to consider the case when b is 0, the 0. Here the 0 vector, this means 0 is a vector of all zeros. Okay, so we call this case, we say that the equation is homogeneous, i.e. the equation is ax is equal to 0, and we call this a homogeneous linear system. Homogeneous linear system. Okay, so for homogeneous linear systems, notice that x equals 0 is always a solution. So notice that x equals 0 is always a solution for a homogeneous system. Of equations. Okay, so this is square or non-square. I mean, we're considering the square case here. 0, because a times 0 is always 0, so there's no problem with that. So in this case, Gaussian elimination gives us the following two cases. So If the determinant of A is equal to 0, before we had no solutions or infinitely many solutions. No solutions case cannot occur since x equals 0 is a solution. So we have infinitely many solutions. And secondly, if determinant of A is non-zero, then you have a unique solution, and that unique solution must be x equals 0. So x equals 0 is the unique solution. Okay, so this is what Gaussian elimination tells us about homogeneous linear systems. Okay, so now let's talk about inverting an invertible matrix. Okay, so suppose that determinant of A is non-zero. I mean, invertible matrix means that its determinant is non-zero, so that's an equivalent condition. So suppose that determinant A is non-zero. Okay, so of course A is a n by n matrix. So how do we find A inverse? So we know that A is invertible. How do we find its inverse? Okay, so we need to solve the system of equations AX is equal to the identity. Okay, so this is a little different from the kind of systems we've been solving before. Here the right hand side is also a matrix. So in fact the unique solution of this is X is equal to A inverse. So the X equals A inverse is unique solution. Okay, so in fact Gaussian elimination will tell us how to find X, so we can apply it in this case as well. So let's see how this works. So let's write X is x1, x2 up to xn. So here each xi is a column vector. Each xi is a column vector. Okay, so then Ax is equal to I is equivalent to the n equation. So so when you multiply A by X, you multiply by its columns in turn. So it's A times X1 is the first column of the identity matrix, which is E1, let's call it. So this is 1 and the rest are zeros. And so that's AX1, AX2 is equal to E2. And this is 0, 1. And this is zeros below it, and so on. Up to AX n is equal to En, and this is 0 up to 0, 1. Okay, so now notice that so since A is invertible, and we've been considering solving systems like this, so AXI is equal to EI. The augmented system of this is AEI. And we know that by elementary row operations, we can convert this into the identity, and on the right hand side we're going to have precisely A inverse EI. Okay, so let me see, maybe I should have written that below here. So this we convert this into identity and A inverse EI. Okay, so by elementary row operations we can convert A into EI, A into the identity matrix, and then the right hand side gets converted into A inverse EI, and A inverse EI is precisely the this is precisely the ith column of A inverse. So this is the ith column of A inverse, in fact. Okay, so we can see that if you apply, so if we apply row operations, it follows. I mean, if we sort of put all these together, it follows that if we apply elementary row operations, to AI until we get the identity on the left hand side. We know we can always get the identity, and we get some, let's say, some M on the right hand side. Then each column of M must be the corresponding column of A inverse. So in fact M must be A inverse. Okay, when we apply row operations to this to get, we know we can always get identity on the left. The thing we must have on the right hand side is A inverse. So elementary row ops. Okay, so and we call this the Gauss-Jordan method for computing A inverse. Jordan method for computing A inverse. So note that if A was not invertible, if A had not been invertible, by elementary row operations, we would eventually get a row of zeros in the first part before the vertical line. So we would eventually get eventually transform A into a matrix with a row of zeros and then would be stuck, right? So you don't need to check that A is invertible first. If you apply Gauss-Jordan, either A will eventually be converted into a matrix with a row of zeros, or you will get the identity matrix. If you get the identity matrix, then after the vertical line, you will have A inverse. Okay, so a quick example. So find the inverse of the matrix A equals 1, 2, 3, 0, 1, 4, 5, 6, 0 using Gauss-Jordan method. And so we start off here with the augmented matrix. So 1, 2, 3, 0, 1, 4, 5, 6, 0. And we put the identity on the right hand side. And now we apply elementary row operations to this. So there's a long sequence of elementary row operations. I'll tell you the first one. So the first one, we have leading ones here, and we want to get something non-zero. We want to get 0 entries below these leading ones. So we will take minus 5 times row 1 and add this to row 3. And that will give us something like, so 1, 2, 3, 1, 0, 0, 0, 1, 4, 0, 1, 0. And the last row will become 0. This is going to be minus 4 and minus 15 and minus 5, 0, 1. Okay. And then we proceed like this. So the first column is okay, and we first convert this into the first part of this augmented matrix into row echelon form, and then into the identity. So let me not write down the steps as an exercise. So eventually you'll get the identity matrix on the left, and on the right you get something like this. You can check this. And the method tells us that this matrix here is precisely A inverse. So this is the inverse of the matrix that we've been looking for. Okay, I'll stop for today here.